Okay, well, okay, got it. Well, good afternoon, everybody. I'm very pleased to give this talk. Bernhard asked me to say something about quantum devices as the first lecture in a series of lectures that we anticipate we will have over the next, I guess, few months or a year. I'm going to focus really on my own topics of interest, Spintronics and Ionitronics, and I'm going to say something about those fields, again, mostly focusing on my own work over the last several years. And as you know, I'm from the Max Planck Institute of Microstructure Physics. Over the last 5 years since I came, we've completely rebuilt the institute. We have myself and two other directors, Joyce Poon, who's in nanophotonics, and Jinliang Feng, who's in organic chemist, who's very much involved in the graphene program and is interested in a wide variety of devices, quantum devices using organic materials. So this is what I'm going to briefly discuss, and I'm happy, anytime you have a question, please don't hesitate to interrupt. So I thought, just by way of introduction, rather than giving a lot of foils, I would just have one foil where I want to basically discuss what are some of the questions that we might want to address in terms of a discussion about quantum devices. And so the first point is our graduate school is about quantum materials. And materials really are the basis, can be the basis of entirely new devices and technologies, both because of new physical phenomena that might be discovered, or by engineering materials to have properties that are designed to enable new devices and new technologies. And so I thought I would just put down a series of questions that we might want to ask during this series, or you might want to ask, or you might want to ask that there be lectures about some of these aspects. And so I think we do need to discuss how can quantum devices help us to solve the most pressing issues of today. And of course, this certainly includes, for example, climate change, how do we go beyond existing types of computing systems, etc. And of course, at the same time, can we engineer the properties of materials and devices that we need to solve such critical problems? And I think an important point here is that such materials or devices often have to have more than a single characteristic property. They have to be multifunctional and need to satisfy typically many different criteria in order that they have utility in a quantum device or quantum technology. For example, they might need to satisfy certain environments. They might need to operate over a wide range of temperature or pressure or whatever. And then related to this, maybe it's not really so much connected to quantum devices or materials. Are the materials sustainable? So sustainability, there's been a lot of discussion by some of the directors in our various institutes about what should we do about sustainability. Materials, many of these materials that we might want to use are in short supply. Therefore, we need to imagine building quantum devices using materials that are sustainable. And by sustainable, this also means that can we recycle them because of the limitations of these materials, again, to reduce impact on the environment. So these maybe are questions that go far beyond what I'm going to talk about today. A separate set of questions might be, how can we accelerate our search for materials with these novel properties, both experimentally and theoretically? And certainly it's true, for example, for topological materials, that theory has often come first, and then experiment has followed the theoretical predictions. And I think a very interesting question is, can we use accelerated computational models and techniques to identify novel materials that could sustain novel quantum devices? And certainly I'm involved in the collaboration with Andre Benevig and Claudia Felser, where Andre and his colleagues are using really advanced computational techniques, theories, to identify properties of materials that are available in databases today. For example, there's a database of all the known inorganic compounds. It's about 500,000 materials. And today it's possible to take all 500,000 materials and calculate certain properties to maybe identify materials with, for example, novel topological properties that might have novel fermions or quasiparticles. And this approach has been, I would say, extremely successful, even in the last 2 or 3 years. However, at the same time, I did want to mention that quantum devices often involve interfaces between different materials. And interfaces are super interesting because they can have emergent or novel properties beyond those of the materials from which the interface is formed. And it turns out this is, I think, a very interesting problem because it's very difficult often to calculate the properties of an interface, even difficult to calculate the structure of the interface or the separation of the two materials that might form the interface. And at the same time, it's super interesting that surfaces and particular terminations of crystal terminations can have unique properties. So again, with Andre, he and a postdoc here in my institute, Wangfeng Xu, have calculated using some very interesting models. They've taken all the insulating materials in this database, and they've identified all the materials which should have surfaces or terminations that should be metallic. And I think this is super interesting. And they've done this by identifying surfaces where the electron wave function is not localized at an atom, but is in between. So when you cut the material through those locations, then automatically it will be metallic. So I think this again is a very interesting approach to finding materials which might have metallic surfaces, for example. And we're very interested here in trying to search for superconducting materials that might involve such a termination, plus combining such a termination with another material that could give rise to interesting pairing mechanisms. So this is very different from the approach that was discussed this morning about using photons to excite, let's say, phonons, and to try to develop then non-equilibrium superconductivity, although that's super interesting. So related to this, we have to worry about defects. Defects often determine properties, in particular, transport properties, often dominated by scattering, and controlling scattering mechanisms and is super important. For example, I'm going to discuss the spin Hall effect. We've recently discovered some materials which are very resistive. We take material A and material B, both of which are very good metals, but the resistivity of a combination can be 500 times higher than those of these end members. And we've discovered that these materials, which have very high resistivities, can also have very, very large spin Hall angles. In fact, we've discovered materials which have the highest spin Hall angles of any conventional metal, not topological metal, but a conventional metal. Then another question I wanted to bring up is collections of devices often have properties beyond those of the individual devices. And so these emergent properties are, if you like, of networks in some sense, are super important. And this applies particularly to quantum computing. It's okay to build an individual qubit, but really to explore quantum computing, then one needs a series of quantum bits, maybe 100. And this means you need an engineering solution. So engineering, I think, is super important in terms of developing quantum materials and quantum devices. And finally, another point I wanted to briefly make is that today, because of the extremely fast optical communications that are possible, then as you know, the cloud is where 70% of all the data is stored today. It's in the cloud, it's no longer local. And this also means that we could build devices like quantum computing systems that might operate in highly special environments, not accessible in somebody's home or a factory. And this means we can imagine new phenomenon and new quantum devices. And so something I'm not going to talk about, but maybe later on in this series about quantum devices, I'd be happy to talk about some recent discoveries we've made, which involve the concept of triplet supercurrents at interfaces. And these triplet supercurrents in superconducting materials can carry spin angular momentum. And we're very interested in, can we use these triplet supercurrents at ultra low temperatures to manipulate, for example, magnetization? That's never been demonstrated. That's something we're working on. And we've also discovered recently, there was a very interesting talk this morning about non-reciprocal effects. And we've discovered a non-reciprocal Josephson diode effect in a Dirac semi-metal by proximity with a superconductor, in which we can see that the Josephson current below which you see the supercurrents, the critical current it depends on whether the current flows from the left to the right or right to left, in otherwise what looks like a highly symmetric device. So I think this concept of interfacial superconductivity is very interesting. Anyway, I'm not going to talk about any of that. These are all ultra low temperatures, 10 milli-K experiments that we've recently carried out, but I'm not going to talk about that. I'm going to talk, as I said, about Spintronics and Ionitronics. So those were just some brief questions. Now I want to talk about spintronics. And again, I just want to put this in context. Materials are super important. And, you know, the ages of man are defined by materials, the Iron Age, the Bronze Age. And we, for the last 40 years, have lived in the Silicon Age, which, as you all know, is coming to an end. And with the ending of the age of silicon, there's a huge opportunity for new quantum devices to take over from the existing silicon-based, essentially field effect transistor that has powered computing systems for the last 40 years. And so then there's huge interest in two new forms of computing that was mentioned this morning in the context of spintronics, neuromorphic computing. Actually, I'm not going to talk about that, but it's a very interesting concept of using spin non-collinear spin textures to imagine building reservoirs of spin systems for neuromorphic computing. And there's also, I already briefly mentioned, quantum computing, which again involves very novel physics. And this has so many components to it in terms of error correction and the developing of appropriate quantum algorithms, as well as engineering massive numbers of qubits. So this is a very enormous, challenging problem. And I think you all know that the German government is investing 2 billion euros to build 2 distinct quantum computing systems in Germany over the next 5 to 7 years. And then finally, I want to just make a comment. Oh, is that a question? Maybe not, so I carry on. Okay, so I'm going to carry on. And then I wanted then, as I said, we need to go beyond using simple electrons, and maybe we want to involve the electron spin, or if there's time, I want to briefly discuss this concept of using ions and ionic currents to electrochemically modify materials to enable us to build new types of devices. And at the same time, at least in terms of computing, the systems have largely been two-dimensional. You've had an array of transistors in the surface of silicon, and all the connections are three-dimensional, but the wiring is three-dimensional. But the innate device consists of a two-dimensional array of silicon MOSFETs. And similarly, many of our memory and storage devices are similarly innately two-dimensional with connections in the third dimension, but effectively a two-dimensional layer of the actual devices themselves. So then building three-dimensional structures is very important. And in my own institute, we've developed what we think is the first super resolution double photon 3D printer. And we're building very interesting chiral structures and showing that the properties of these structures depend on whether we form left-handed or right-handed chiral structures. Again, it's not something I'm going to talk about, but we're very interested in looking at a combination of geometrical chirality plus, for example, spin chirality, and we can see that the two interact in extremely interesting ways. So now if we spend a few minutes on spintronics, the first talk this morning discussed some very interesting non-collinear spin textures. If you go back in time, spintronics, it's a field maybe 30 years old, and the most important impact of a device, a quantum device in spintronics, is a device actually that I invented. It's a spin valve device where you have two magnetic layers separated by a thin metallic layer, and the conductivity of this sandwich depends on the orientation of the magnetic layers. So you could use this as a sensor to detect magnetic fields, and this has been used in magnetic disk drives since for more than 20 years. And this has enabled us to detect much smaller areas of magnetic material. And in this cartoon, on the right-hand side, these blue and red regions correspond to regions that are magnetized in a thin magnetic layer, which is distributed on a glass disk. And these regions today would be approximately 20 nanometers in extent, and are detected using a magnetoresistive sensor that was a metallic sensor for 10 years, but has been since 2007 a magnetic tunneling junction. And this is certainly a quantum device. The metallic tunneling junction, as shown in this cartoon, consists of these two magnetic layers shown as pink and red. These are magnetic layers that will be magnetized in parallel or anti-parallel to one another. And because the electrons that tunnel through the gray insulating layer are spin polarized, because the density of states in the magnetic material is spin polarized, the current, the tunneling current, is innately spin polarized. And it can be nearly 100% spin polarized. And that means that because the electron spin is conserved in the tunneling process, the electrons can only tunnel into states which have the same spin orientation. So when the layers are made of the same magnetic material, these two red layers, and they're oriented parallel, then current can tunnel. But when they're oriented anti-parallel, effectively you can turn off the current. And this is like a tunneling valve. These are these sensing devices then have been used for the last 20 years in, well, not almost 20 years, 14 years in magnetic disk drives to detect information. And they also form the basis for a magnetic memory, a magnetic random access memory, in which these devices would be, as shown in this cartoon, placed at the intersection of wiring layers above and below the tunneling junction. And then you can read these devices from their resistance, or you can write them by passing current through the devices. And the current, which is spin polarized, carries spin angular momentum. And this spin angular momentum can switch the direction of the magnetization. And this, again, is a very interesting phenomenon in spintronics, and really has been one of the most exciting developments in spintronics for the last decade or more, in the sense that this concept of spin, the transfer of spin angular momentum, enables one to write magnetic bits in this way, in ways that make possible very interesting devices. So next, I want to just make a brief comment that the time for taking a new phenomenon or a new material from the laboratory into a real device can be very long. And so, for example, in the bottom part of this foil, I just mentioned that this magnetic random access memory that was briefly mentioned this morning by the first speaker is something that we proposed in 1995. And even though we actually, when we proposed it, the tunneling junction devices had resistance values that were 100 million times too large to be useful. Then nevertheless, they had very, very tiny tunneling magnetoresistance values, less than 10%, which is not big enough for device applications. Within a few years, we could demonstrate that we could build devices using new materials, which had 100 million times lower resistance, which means you need extremely thin tunneling layers, the insulating layers of today. In a real device, they will be less than 1 nanometer thick. And you need to build then a very ultra thin insulating layer in which there are no defects. So the electrons tunnel directly from the magnetic layer to the other magnetic layer without any tunneling through defects in that insulating layer, which is very challenging. Nevertheless, even though we demonstrated the basic concept in 1999, the tunneling magnetoresistance wasn't big enough until a few years later. We demonstrated that using a new type of tunneling barrier, we could see tunneling magnetoresistance values at room temperature of several 100%, which is what is needed to build a true high-performance magnetic random access memory. And then we demonstrated that in 2005, but actually it was only in 2019, 2 years ago, that Samsung actually was the very first company to announce that they could manufacture a high-performance, CMOS compatible spin transfer torque MRAM. And that now is something that if you want to build chips, Samsung will provide that technology for you for an embedded non-volatile memory, which has higher performance than is possible with any other technology today. At the same time, on the top of this foil, briefly, it turns out that this spin valve device that I invented, it actually took only a few years, 7 years from invention to its application in a magnetic disk drive, which is actually very fast for a new phenomenon or a new material. And that enabled a 1,000-fold increase in the storage capacity of magnetic disk drive. And now, today, that is what is used, as I said, for storing nearly all the digital data in the world. But like the CMOS technology, the scaling to greater volumetric capacities is very tough, and alternatives are needed. So this is a huge opportunity also in digital data storage, to invent new quantum materials and devices that could enable new forms of storage. And one of those is this racetrack memory. Now, something also I proposed in 2002, and we demonstrated this in 2008 for the first time. And what is it? Is you can see in this cartoon, you have basically a vertical, if you like, wire of magnetic material, and the blue and red regions are magnetized in opposite directions, perpendicular to the racetrack, and the boundaries, the domain walls between these regions are moved by passing current through these domain walls. And it turns out the current then, if it's spin polarized, can carry spin angular momentum and can provide torques on the domain walls. And the most important point is that all the domain walls can be moved simultaneously, synchronously, at the same velocity in the same direction. But when the current is reversed, they can move in the opposite direction. Therefore, you can take a series of domain walls, maybe 100. These 100 domain walls would correspond to zeros and ones. And you can move them around this magnetic racetrack to individual reading and writing devices built into or around the racetrack. And this means that you can increase the capacity of such a device by about 100 times compared to any other device in the same area of a silicon wafer, which is the most important parameter. So we could build a truly solid state device with no moving parts. You know, a disk drive is fundamentally a mechanical device, which this racetrack memory would have the capacity of a magnetic disk drive, but it would be approximately 1,000,000 times faster and use considerably less energy, perhaps 2 orders of magnitude less energy. So this is truly interesting. And actually, we have a program here in my institute. We're working with Samsung is funding us to carry out research to explore how small a racetrack we can make and to develop the properties needed to make it into a new technology. And I think the last 2 years we've been funded, and we have 1 more year of funding. We've made enormous progress in demonstrating we have racetrack devices now on the 50 nanometer width with domain walls moving at about 1 kilometer per second. And we've demonstrated at least we can position domain walls to an accuracy of about 40 nanometers. It needs to be a little bit better. And the other important criterion is the critical current density above which the domain walls will move. I'm going to briefly come back to that. And we've also made enormous progress in an understanding in reducing that critical current density to values that would make such a racetrack potentially possible. So in principle, we can build a racetrack memory now that would enable us to replace the densest solid state memory today, which is vertical NAND flash memory. And we could also use it to replace the fastest memory today, which is static random access memory. So it has very interesting applications all around. And I think this is a very interesting quantum device that is based on very recent developments in the physics of manipulating domain walls. I want to tell you briefly a little bit about how domain walls are moved. So when we first started working on racetrack, this is the concept that we were interested in. If you take a magnetic material shown in blue and you introduce current from a battery, the battery will have equal numbers of upspin and downspin polarized electrons. But in a magnetic material, as was originally demonstrated by Neville Mott a long time ago in the 1930s, then the current becomes spin polarized because upspin and downspin electrons are scattered at different rates. It's a very simple concept. The current then in a ferromagnetic material or even a ferrimagnetic material is carried predominantly by electrons of one spin orientation. So for example, let us take an alloy of nickel and 20% cobalt. The current is approximately 70% carried by electrons of the majority spin polarization. So what does that mean? First of all, that does lead to giant magnetoresistance. But more importantly, if you look at the cartoon below, this is actually a cartoon from Sademichi Maekawa, who's a theorist in Tokyo University, now who's retired. But nevertheless, when you can see that the current then is spin polarized. That's shown by the moving electron spin, but the fixed magnetic arrows correspond to the domain wall. So you see on the left side, the moments are pointing to the right, and on the right-hand side to the left, and in between, they're rotating. And it turns out that on the nanoscopic scale, domain walls are basically objects, nano objects. They have mass and they have momentum. So by passing this current of spin polarized electrons, then the electron spin will rotate and deliver a quantum of angular momentum to the domain wall. And approximately one electron can rotate one atomic spin. And this means you need enough current to manipulate all the moments. And it turns out that means that in this nickel cobalt system, you need a current density of about 10 to the 8 amps per square centimeter to move the domain walls at approximately 100 meters per second. That basically is the limit, the upper limit for this physics to work. In other words, you transfer spin angular momentum from the current directly, it's polarized by the magnetic material and then passed into the domain wall. The domain wall will move at that speed. It turns out that for applications that may not be fast enough, I'm going to come back to that. But this was very exciting development, and in a paper we published in Science in 2008, then we demonstrated we could use this technique to manipulate and move domain walls. And so in this case, we measured the numbers of the domain walls in this racetrack. I don't know if you can see this in A. This is the wire, and then there are some perpendicular electrical contacts to that wire. We're simply measuring the resistance of the wire at low current, and at higher currents, the domain walls will move all in the same direction. And then it turns out that the resistance of these wires is almost, if you like, quantized, not really quantized, but has a fixed value per domain wall. And so you can see in B, the resistance will drop when we introduce a domain wall and drop again when we introduce a second domain wall. And then as we pass current, then that second domain will be eliminated to the right. And so we only have one domain wall and so on. So we can actually write a series of domain walls and detect them. This was the first time that anybody had demonstrated one could use current to move domain walls all in the same direction. So this was a very interesting development, I think. But this actually, it turns out in the last 10 years, it turns out that this concept of racetrack memory is actually much more exciting than we realized at that time. Because as I said, the maximum velocity we could anticipate using this spin transfer torque from the volume of the material is about 100 meters per second. At higher current densities, the wires would get too hot. In the last 10 years, and again, I don't really have enough time to discuss all this work in detail, but you can see from some of the publications on the right-hand side that we have been consistently publishing, even this year. We've had several papers, and last year, and what we've discovered is that we've actually, I like to say, we have 4 different types of racetracks with different physics. And this has led in just the latest generation to the ability to move these domain walls using a different physics I'm going to briefly discuss at speeds of more than 1 kilometer per second. That's like 10 times faster for the same current density than was possible 10 years ago using physics that wasn't known at that time. So I think that's a very exciting development. All this new physics and all these new materials has led to this very interesting development that makes racetrack memory 10 times more exciting and interesting than it even was 10 years ago. So I think this is fantastic. Now, I don't have time to discuss all these memory technologies or these racetrack memories, but I just want to give you kind of a flavor. I mean, later on, I could give more discussion if anybody's interested. But basically, there are 4 major or 5 ingredients to racetrack. Now, one of them is a very simple concept. We're engineering materials and interfaces. As I mentioned in my very first foil, I think interfaces are really one of the most interesting material systems to explore. Turns out if you take a simple material, a layer of cobalt, and you make it very thin, which means 1, 2, 3 atomic layers, and separate it with ultra-thin nickel layers, that cobalt-nickel combination demonstrates a very strong perpendicular magnetic anisotropy. Cobalt and nickel are super soft cubic materials where the moments basically will lie in the plane of the racetrack because of demagnetizing the fields. But in the case of these super atomically thin multi-layered systems, the moments will rather be oriented perpendicular to the interfaces because of the broken symmetry of the interfaces. And this is very interesting also. This actually was theoretically predicted many years ago and experimentally verified again many years ago when the concept of perpendicular magnetic anisotropy was a topic of considerable interest. Now it's more like it's accepted and we could use it as a technology to make racetrack memory. Now, why do we want perpendicular magnetic anisotropy? Because that anisotropy means that the size of the domain wall will be shrunken, and it will be shrunken by 100 times compared to the domain walls I just mentioned that we were moving. Those domain walls are either transverse walls or vortex walls, and their size is of the order of 100 nanometers. And it turns out they're highly flexible. They can be microns in extent. However, using this perpendicular magnetic anisotropy, then the moments either want to be up or down. And therefore, this means that the wall, the domain wall, will be much smaller. And the size of that domain wall will depend on the ratio of the exchange, Heisenberg exchange, and the anisotropy itself. The bigger the anisotropy, the smaller the wall. We estimate the domain walls using this cobalt nickel multilayer are of the order of just a few nanometers in extent. That's one interfacial concept that's very important. Now, another interfacial concept which is very important is this concept that, again, a broken symmetry at an interface between a magnetic material like cobalt or nickel and an underlay, another metal layer, which has a lot of spin-orbit coupling, leads to something called the Dzerzhinsky-Meurier exchange interaction. This was invented in the 1960s to explain spin class systems. And Dzerzhinsky-Meurier independently came up with this concept. But nevertheless, the point is that the broken symmetry means that there is a new exchange interaction which is mediated by that heavy metal. Let's say it's platinum. Then the cobalt atoms on top of the platinum, broken symmetry, exchange interact through platinum. And this means that they want to be perpendicularly oriented to one another. And they want to be perpendicularly oriented in a clockwise or an anti-clockwise fashion. There'll be one or the other. Let's say with platinum, it's clockwise. If you use tantalum, it would be anti-clockwise. What does that mean? Well, then actually, this morning, it wasn't really discussed in the very first talk, but these skyrmions will have a chirality. And the chirality of the skyrmions is derived from this chiral Dzerzhinsky-Meurier exchange interaction. And so in this cartoon, which I'm afraid is very poor quality cartoon I've made, you can see a red magnetic region where the moments are pointing up on the left and on the right, and in between a domain where the moments are pointing down. This is from the perpendicular magnetic anisotropy. And if we build that cobalt-nickel-cobalt sandwich, which is only 1 nanometer thick, on top of a platinum layer, then within the domain wall, the moments will rotate in a clockwise direction in both domain walls. So if you look in the cartoon on the left side, the red moments rotate in a plane perpendicular to the domain wall, showing the green arrows in the middle pointing to the right. But when the blue moments rotate from down to the red up on the right-hand side, then the green arrow will point to the left. And this is a super important and interesting phenomenon, which is very important for the motion of these domain walls using spin-orbit torques, which was also mentioned this morning briefly. And so this is another interface-derived, in this case, exchange interaction. So it turns out the Dzerzhinsky-Merer interaction you can also see in bulk materials with broken inversion symmetry. I'm going to come back to that again later. And then finally, I think number 3 here, this proximity-induced magnetization is also super important, which means that the cobalt or nickel layer on top of platinum causes the platinum to become magnetic. But the magnetization in platinum can be quite large. At the interface platinum moments will have 1 or 2 Bohr, 1 Bohr magneton, but it decays exponentially into the platinum with a typical decay length of about 1 nanometer. So it's a very important effect. So 1 nanometer of cobalt, nickel, cobalt on top of platinum, the magnetization will be increased by approximately 30% because the platinum will have a moment equivalent to 30% of the cobalt, nickel, cobalt sandwich. So it's an enormous effect. Then finally, there's another very important effect called the spin Hall effect. And that means that in materials with strong spin orbit coupling, you can convert a charge current to a chiral spin current. I'm going to come back to that briefly later on, although I'm not really going to discuss it in any detail. But the most important parameter is something called the spin Hall angle, which is the ratio of the spin current that is generated to the electrical current that is passing through that material. And typical materials like platinum have spin Hall angles of the order of 0.1. Recently, we've discovered some new materials, which I'm not going to discuss, which have spin Hall angles exceeding 1.0. And I think this is very interesting. These are conventional materials. I'm going to come back to that briefly later on. And then I'm going to talk briefly about this synthetic antiferromagnet, which corresponds to our ability to create spin textures artificially by taking advantage of coupling of magnetic materials through proximity-induced spin density waves in nearly all materials. So I'm going to come back to that briefly, if there's time. So now I want to come back to, then I wanted to talk, I've talked about this, Dzerzhinsky-Merer interaction, I briefly mentioned. This sets the domain walls, as I've shown here, in a perpendicularly magnetized material on top of platinum, on top of tungsten, on top of many other materials to be chiral, clockwise or anti-clockwise, and these are called nail domain walls. Alternatively, if you have no such Dzerzhinsky-Merer interaction or different symmetries, then the walls can be block-like. In a block-like wall, the moment rotates from an up direction to a down direction by rotating in a plane parallel to the domain wall, not perpendicular to the domain wall as in a nail wall. And this is, I'm going to come back to that briefly, but block walls can also have a chirality, which is clockwise or anti-clockwise. And again, I wanted briefly just just introduce the spin Hall effect without really discussing its origin. Conventionally, on the left-hand side, if you pass an electrical current through a material in the presence of a large perpendicular magnetic field, then Lorentz forces on the electrons causes a buildup of charge to the left or to the right. And that charge current is the ordinary Hall effect, and of course is determined by the density of carriers in the material. But there's a very interesting effect called the spin Hall effect. It's actually known about, experimentally discovered maybe 15 years ago, was predicted in the 1960s, and then Hirsch in San Diego again reinvented it, and then it was discovered by David Oshlom in a semiconductor material where the effect was something like 0.1%, a very, very tiny effect. But it turns out recently it's been shown by ourselves and others that the spin Hall effect, the conversion of charge current to a spin current, can be very large in some metals, much larger than anybody had predicted. So this is a case where theory did not predate the experiment. Anyway, if you see in this cartoon, what happens? The yellow arrow shows you the charge current passing through a material, typically with large spin-orbit coupling. What happens then is the electrical current is converted through intrinsic or extrinsic scattering to a spin current that flows chirally around the circumference of that wire, as shown by these arrows. And you basically accumulate a certain amount of spin density on a surface, and so the spin current is flowing perpendicular to the current, and the polarization of that spin current is typically perpendicular to both. Now, why is that interesting? So it turns out you can use then a metal layer like platinum to convert electrical current into spin current. Then the spin current can flow from that platinum into a magnetic layer on top, like the cobalt, nickel, cobalt sandwich, and to be a pure spin current without any charge current. That means that there's the equal numbers, electrons flowing, let's say, in one direction would spin up, and the opposite direction would spin down. So there's no net current flow, but there's a spin current flow. Spin current carries spin angular momentum, and that can deliver torques. And that's how the spin orbit torque is derived. Now, of course, it's much more sophisticated, and there are many interesting aspects to this spin orbit torque that I don't have time to discuss. But as I said, the conversion efficiency in metals, which was believed to be tiny just maybe 5, 6, 7 years ago, is now recognized to be in the order of 10 to 30%. And that's large enough to create very large spin orbit torques. And so I just wanted to mention briefly, in our own work, we actually demonstrated 3 or 4 years or 5 years ago that tungsten with some oxygen generates a spin Hall current of about -0.5, which is the largest known until our even more recent work, which is unpublished, where it exceeds 1. And there's been a huge amount of interest in topological materials for which it's believed the spin Hall angle can be significantly larger. Although to me, I don't think there's so much convincing experimental work that really demonstrates large spin Hall angles. It's difficult to define or measure the spin Hall angles because in these topological systems, the currents are flowing in states at the interface or the surface of these topological materials. Nevertheless, very interesting, important developments just in the last 10 years about metals that can now show these large spin Hall angles, therefore can generate large spin Hall orbit torques, and therefore can be exceedingly useful for quantum devices. Now, I wanted to finally mention, like as I mentioned before, multifunctionality, the very first foil. And it turns out in magnetism, a property that is very difficult to control are long-range dipole fields. So you all know that bar magnets will give rise to demagnetizing fields. And this means in a racetrack memory in particular, these domains can interact with one another, or magnetic domains in one racetrack can interact with domains in another racetrack. So how do we avoid this problem? And it turns out we could use something called a synthetic antiferromagnet. And actually, it turns out this was something I invented many years ago and is the only reason why spin valve sensors in magnetic disk drives could operate. Because on the nanoscopic scale, if you have a sandwich of 2 magnetic layers, those 2 magnetic layers on the nanoscopic scale, which is necessary for building these sensing devices, will interact with one another through the fringing fields from the edges of those elements. So it's impossible. The magnetic layers will either be oriented parallel to one another if they're perpendicularly magnetized, or they'll be oriented anti-parallel in the sandwich of magnetic layers in which they're magnetized in plane. But a racetrack, then, we do something else. What we do here in this synthetic antiferromagnetic racetrack is to make 2 racetracks. So one of these cobalt, nickel, cobalt sandwiches, and we separate it from a second identical one by an ultra-thin layer of ruthenium shown in yellow. And why do we do that? Well, it turns out a long time ago, something I showed was that ruthenium and nearly all the transition metals in the periodic table, as well as the noble metals, give rise to a long-range magnetic interaction, which is oscillatory. And it's due to the fact that by this proximity-induced magnetization, nearly all the transition metals become magnetic, but they become magnetic in a very special way. They form a spin density wave from the interface with the magnetic layer. And that means the ruthenium develops a spin polarization that is oscillating from up to down across the ruthenium layer with a period that's determined by the Fermi surface and essentially so-called spanning nesting wave vectors of that Fermi surface. It turns out in ruthenium, this period of oscillation of the spin density wave is about 1 nanometer. So that means every 1 nanometer, the ruthenium spin polarization will rotate from up to down, where the polarization is set by the interface exchange with a magnetic layer, in this case, cobalt. And this means then a second cobalt layer, which is placed about 7 angstroms from the first one with an intermediate layer of ruthenium, will be coupled antiferromagnetically. This coupling strength is actually very large. It's about 1% of the exchange in the cobalt layer, which is huge. And this means that the one racetrack layer moment in the bottom will be exactly mirror imaged in the racetrack above, as shown in this cartoon. So here you can see in the LM, the lower magnetic racetrack layer, which is a cobalt, nickel, cobalt sandwich, has a domain wall where the magnetization is rotating from the blue direction to the right direction in this clockwise direction. And then the racetrack on top, the upper magnetic layer, will have exactly the opposite mirror image domain wall with the same chirality. And it turns out then in aggregate, there's no net moment in that synthetic antiferromagnetic racetrack. And this means there's no dipole field. And so there's no longer any interaction between one racetrack and another, or between the magnetic domains in one racetrack. This is super important. And it turns out when we made these racetracks, it turns out we unexpectedly discovered that the very large exchange field, antiferromagnetic exchange field between the upper and lower racetracks gives rise to a new type of torque, which is extremely effective. And it enabled us to increase the velocity of the domain walls as we pass current through the domain wall by a factor of 5. And this is how we achieved speeds of current-induced motion of domain walls using a combination of spin-orbit torques from the spin Hall effect in the lower platinum layer, plus this giant exchange interaction derived from the antiferromagnetic coupling field. So it turns out in this racetrack, you can see velocities on the right-hand side. It depends on the more compensated are the moments in the upper and lower racetrack. And this means because of the proximity-induced magnetization in platinum, the moments have to be adjusted slightly to make them identical. The more identical they are, the faster the moments go. So when the moment is 0, that's the fastest speed, which is fantastic for technological applications. So this is really amazing. And to build a racetrack memory, this is the only way to go, using these synthetic antiferromagnetic racetracks with no long-range dipole fields. And as I said, this is exactly the concept I had many years ago and has been used in a different context in spin valve sensors and tunneling junction sensors. It's also super important for magnetic tunnel junction memory devices. Now, how do we look at these racetracks? And so here in my institute, we have 2 Kerr microscopes we built where we can vary the temperature down to 5 degrees Kelvin. And we use an optical technique where we simply reflect a linearly polarized beam of light from the surface of a magnetic material. And through something called the Kerr effect, the plane of that polarization is slightly rotated in reflection, or one can also look in transmission in what's called the Faraday effect. And we can then basically, as you can see in this upper, I don't know if you can see in this upper picture, you can see a series of black and gray regions. These are regions magnetized up and down on the domain walls. And when we pass nanosecond long current pulses, we apply a pulse, take an image in the Kerr microscope, and then we can just see these sequences of images corresponding to the motion back and forth of, in this case, 20 domain walls. They're all moving at the same speed. In the upper racetrack, it actually consists of a single cobalt, nickel, cobalt sandwich on platinum. And in the lower one, it's difficult to see because here there's a synthetic antiferromagnetic racetrack. The domain walls are moving much faster, but more difficult to see because there's no net magnetization. So finally, I'm not going to say any more about racetrack. Maybe that was too much, but what's super interesting then is that there's a complex interplay of 4 spin orbit derived phenomena that enables us to move a series of domain walls using spin orbit torques at speeds 10 times higher than was anticipated 5 years ago. So I think this is super exciting. I want to then briefly discuss, if there's time, some work on some more sophisticated spin textures, and it really follows a very nice talk by Lucas this morning. And here I just want to acknowledge then students and postdocs in my institute here in Max Planck, and also want to acknowledge that the bulk materials we're going to discuss were made by prepared by Claudia Felser and her collaborators at the Max Planck Institute for Chemical Physics of Solids. And I also wanted to acknowledge my former group in IBM Almaden, and I wanted to acknowledge the theoretical support from Ingrid Mattig and Birger Goebel here at the Martin Luther University, and Daniel Loss and his collaborators in Basel and Tokyo in providing theoretical support for some of this work. So the background here is we want to look at systems which might display large Dierlesinski-Morea exchange interactions, which, as I said, is a vector chiral exchange. And it turns out then a very interesting family of compounds which have a particular symmetry that supports such this DMI are the Heusler compounds. Now, the Heusler compounds basically are cubic materials with 4 interpenetrating FCC lattices. But it turns out the ones that are magnetic display a tetragonal distortion, in which the magnetization now points along one direction, as shown in this middle cartoon. Turns out then, in some cases, if that material contains heavy atoms like platinum or rhodium, then Claudia and her collaborators discovered that there was some evidence that the structure was no longer collinear. So this, if you look in the middle, the basic structure of these Heuslers are manganese, 2 manganese FCC lattices, 1, let's say, platinum, 1 tin. And you end up then with a structure with this tetragonal distortion in which you have planes of manganese and platinum separated, let's say, by manganese and tin. And it turns out, because of the different in local environments of the manganese atoms, they have different net magnetic moments. And whilst each plane of manganese atoms is ferromagnetically aligned, every other plane is aligned antiparallel. But because they have different moments, there's a net magnetization. This is a ferrimagnetic system. And then Jürgen Kübler calculated that for some of these systems, he calculated that perhaps at lower temperatures, the system, instead of being a pure collinear ferrimagnetic system without a plane magnetization, would become non-collinear, where the moments in one of these layers would be oriented at a large angle compared to moments in the other manganese layer. And this was reflected in some of our own experiments with Rana et al. We showed that this led to, for example, a topological Hall effect. So it seemed to be consistent with the notion that there could be some interesting non-collinear spin textures. Before I get onto that, I did want to mention, as I said in the very first foil, it's extremely important to make interfaces. And it turns out that for applications, let's say, in a racetrack, you would need to make these Heusler compounds in a thin film form, and they would have to be very thin. Because, let's say, we want to use a spin orbit torque, then the spin current can only create a certain amount of current, and so the layer has to be relatively thin. And it turns out, before our work, that people had not, even though there was a decade or more work, could not make ultra-thin Heusler compounds with the same properties as the bulk. And the reason is you need them to be atomically ordered, atomically and chemically ordered. And that is non-trivial. However, we discovered a technique that I think is pretty clever. We called it a chemical templating layer technique. And we used a particular family of compounds which have a cesium chloride-like structure, which has a structure with alternating layers shown here on the left as a Z-primed and X-primed layer. For example, cobalt and aluminum. It automatically forms a chemically and atomically ordered structure even at room temperature. So we can deposit these films at room temperature. They will be chemically ordered. And why is that interesting? So now let's take not this ternary Heusler as I mentioned, let's take a binary Heusler like manganese 3 antimony. And it turns out then that if you look on the right-hand side, let's say we have this cesium chloride chemical templating layer formed from cobalt and aluminum. Automatically at room temperature, it forms this fantastically well-ordered cobalt aluminum structure. And then you see we put the manganese antimony on top. Well, the manganese atoms prefer to grow on aluminum and the antimony on cobalt. And so even when we have an atomic step in the aluminum cobalt layer, the Heusler, binary Heusler layer is actually perfectly chemically ordered. And we can see this in this cross-section transmission electron microscope shown in the middle, where in the manganese 3 antimony, the bright white dots correspond to the antimony. And maybe you can't see, but there are some steps in the cobalt aluminum layer. And nevertheless, the manganese 3 antimony layer is chemically and atomically ordered over those steps. So we think this is a super interesting technique to create, and we've demonstrated we can create binary Heusler layers which are only 1 unit cell thick with bulk-like properties. And we were the first to demonstrate this. So I think that's very, very exciting. And now also exciting was we could see in these materials domain walls moving under current. And the current here, again, is going back to Racetrack Memory 1.0, is due to a volume spin polarization. And it turns out these binary Heuslers, you can form them from manganese with combination with germanium or with tin or with antimony. And we discovered that the polarization is bulk polarization of the current through scattering is negative when we use germanium or tin, but it's positive when we use antimony. And this is reflected in the direction in which the domain walls move. You can see in the manganese 3 tin and germanium cases, here is the velocity of the domain wall on the y-axis versus current density. And that there is a critical current density below which the domain walls do not move. So technologically, we need to reduce that to approximately a few times 10 to the 6. Here it's a few times 10 to the 7. And then you can see that above that critical current density, the domain walls will move with increasing velocity, the greater the current. And they move here at speeds which are not so fantastic, of the order of 60 meters per second or 100 meters per second. As you can see in manganese 3 antimony, you can see the velocity takes the opposite sign. That's because the spin polarization of the volume-derived scattering is opposite. So this is fantastic. And these layers, let's say manganese 3 tin here is just 10 angstroms thick, which is just about 1.2 unit cells. Manganese 3 tin, the orange data correspond to a single unit cell of the manganese 3 tin layer being, at the moment, the domain walls being moved in this way. So we think this is very interesting. And just as an aside, it turns out that the sign of the magneto-optic Kerr effect changes sign with the polarization of these, of the bulk polarization. So it's interesting. Then I wanted just to finally, in this regard, mention that we've recently demonstrated that we can actually make a synthetic antiferromagnetic layer, which is perfectly chemically ordered throughout the whole structure using not ruthenium, but another cesium chloride-like structure, ruthenium aluminum. And if you look in this cross-section TM in the bottom left, you can see the chemically ordered manganese 3 germanium grown on the chemically ordered cobalt aluminum. Then we have a ruthenium aluminum again, chemically ordered, alternating layers of ruthenium and aluminum, and then manganese, antimony growing on top. And we can see actually that this ruthenium aluminum spacigate layer gives rise to an antiferromagnetic coupling, and it's also oscillatory in long range. And that's the first time that this has been observed in any such system. So this paper is under review, but it enables us to make synthetic antiferromagnetic racetracks. Well, that was a pretty long aside. And then at this part of the talk, I wanted to mention that over the last 5 years, myself with many colleagues here, we've built what we think is one of the world's most sophisticated systems for making interfaces, basically, using a wide variety of techniques. And again, I'm not going to discuss this in detail, but on the left-hand side, you can see what we call the tube. This, I don't know if you can see my arrow, but here, this long orange tube, which stretches for 15 meters from the left to the right. And to this tube, which is an ultra-high vacuum tube, we built a fully automated robotic system that enables us to extract a substrate from one of 5 deposition systems, and we can then exchange it automatically between these systems under computer control. And these systems we're connected are, on the one hand, here is I don't know if you can see my arrow, but this is in the middle bottom. You can see an oxide and a nitride, 2 molecular beam epitaxy systems connected through their own robotic ultrafast transfer system is made by Vico, connected to the tube. And then on the right-hand side at the top, you can see a PLD, a pulsed laser deposition system, which is made by Privac. And on the right-hand side, you can see angle resolved photoemission system. And Niels Schroeter is a new independent group leader who's taken over this and is incorporating some new laser sources designed so that we can look at the electronic structure of interfaces made in this system. And then finally, we have our homemade Mango system, I call it. And you can see on the bottom more easily, Mango 2, it has about 40 different magnetron and ion beam sputtering targets. And the whole of this system is designed, including Mango especially, that we could rapidly interchange targets because all the targets are behind gate valves. And so we can change those targets without bringing the system up to air. So this enables us to make hundreds of films in a short period of time. That's the idea. We can explore, as I said, we want to accelerate our ability to explore novel materials and in particular novel interfaces. And in the talk this morning, there was some discussion about 2D materials and exfoliation. And so we've built actually a glove box connected to this tube where we can exfoliate 2D materials and incorporate them with MBE or pulsed laser deposition or magnetron or ion beam sputtered films. And I think that's a very exciting possibility that we are working on here. But again, I'm not going to say much about any of that. I think I'm running out of time, but I'm going to then spend the next few minutes on some non-collinear spin textures. And so this morning in this first talk, actually, what was discussed was a nail skyrmion. And a nail skyrmion, then it turns out, very exciting development where people, Christian Fleider in Munich, first discovered a block skyrmion in a so-called B20 material, which is a cubic chiral material. What does it mean? It means you have a material where there's a clear magnetization direction. And then it turns out, instead of having a uniformly magnetized material, under some circumstances of magnetic field and temperature, the ground state consists typically of an hexagonal array of tiny magnetic circular objects. And these can be block skyrmions, in which the magnetization rotates from up direction outside to a down direction in the middle of this object. And a block skyrmion, the wall, circular wall, will have a block wall type, which means, as I mentioned earlier, the wall, the moment, rotates in a direction from up to down parallel to the boundary. Whereas a nail skyrmion, the magnetization rotates from up to down radially, also as I mentioned. So they're very different. And that depends on this Dzelinski-Maria exchange interaction. Actually, what I want to briefly talk about is something totally different, which is an anti-skyrmion shown in the middle. And it turns out that in some systems with lower symmetry, than most of the systems that have been explored to date, then because of the more complex vector components of this Dzerzhinsky-Merer exchange vector, then around the boundary will change from a nail to a block skyrmion alternately as you move around the circle. And those block or nail skyrmion walls will be tied to the underlying crystal lattice, so they're fixed. This is what happens. And then, okay, since I came 5 years ago, actually, I upgraded an existing transmission electron microscope to have a Lorentz capability, which means we can detect the motion of an electron beam that is passed through the sample. This is shown in this very bad cartoon on the right-hand side. The electron beam, which is a 300,000 volt beam, a tiny beam, passes through a lamella of a material, and the beam is deflected to the right or to the left, depending on the in-plane components of the B field. This gives rise to Lorentz forces. And then we can detect that image and detect whatever we have in the species. And it turns out then we could use micromagnetic simulations to calculate these spin textures based on Heisenberg exchange, anisotropy, and the Dzerzhinsky-Merer exchange that we can put in all symmetries. So this is Chengping Ma, one of my now he's graduated, did a fantastic job. And then we can use something called transport of intensity equations to calculate the Lorentz image. And you can see on the right-hand side, the nail skyrmion looks basically like nothing in the microscope, whereas the block skyrmion looks like this white blob. This is so similar. In the first talk today, I suppose that they were imaging the outer plane magnetic component. And then in the anti-skyrmion, we predicted we would see this 4 cloverleaf-like structure with 2 white blobs and 2 black blobs corresponding to increased or decreased intensity of this transmitted electron beam. And so we actually, this is some work by Ajay Nayak, who was a postdoc in my group. Prior to that, he'd actually been a postdoc with Claudia in Dresden, and now he's back in India. Anyway, after a huge amount of work, we were the first to see this anti-skyrmion shown in here in Halle in the microscope that we had at that time, which, as I said, we modified so we could do this Lorentz imaging. And we can do it as a function of temperature and field. And if you look in C, you can see this array of what are a hexagonal array of these anti-skyrmions. And then it turns out if you increase the outer plane magnetic field, eventually they will disappear. And they are stable, these anti-skyrmions are stable over a certain range of temperature magnetic field. I want to briefly discuss that. Similarly, how do we explore these? Well, we use a technique called focused ion milling to extract a ultra-thin layer from a single crystal provided by Claudia and her collaborators. And then we can, for example, change its thickness. And it turns out, I want to briefly discuss this, it turns out that unlike the block skyrmions originally found by Christian Fleiderer, these objects, these anti-skyrmions, the size and the phase diagram depends very much on the thickness of these lamella. So if you see ABC correspond to 3 different thicknesses, they don't vary by much. But so on the left is a large outer plane magnetic field, then it becomes uniformly magnetized. As that field is reduced, as we move more and more to the right, you start to see these anti-skyrmion objects, but at different fields depending upon the thickness of the layer. And then eventually, on the right-hand side, at the lowest and 0 Tesla in this case, you can see very clearly, instead of these little nanoscopic objects, you see white and black lines. And this corresponds to a different spin texture. It corresponds to a helical spin texture where the magnetization is rotating from an up direction to a down direction with a single period. And in the case of the anti-skyrmions, the helical period is connected to the direction in the crystal lattice that favors block walls. So there are 2 perpendicular directions. which favor block walls, which has the lowest dipole energy. And these are the two perpendicular directions in which we see these helical structures. And now it turns out then we've explored widely the phase diagram as a function of temperature from left to right and as a function of increasing magnetic field. And unlike the skyrmion systems, we see anti-skyrmions over an extremely wide range of temperature and magnetic field with some significant hysteresis. This is a huge advantage for quantum devices that we might want to build from such systems. And I want to compare this then with some very beautiful work by Tokura's group, who originally showed that in another B20 system, which is iron germanium, very closely related to manganese silicon. And if you look at the phase diagram, again, in F, you can see y-axis is the perpendicular field, the x-axis is temperature, and the red region is where they see the skyrmions. And they found that the very thinnest layers, 15 nanometers at the top, they see the widest range of temperature, magnetic field stability. But as they increased the lamella to 75 nanometers, you see the region, the red region of skyrmions nearly disappears. So I want to contrast that then, first of all, to some micromagnetic simulations that Changping Ma carried out. And he showed, and this is, I'm afraid it's not so clear, but in this case, the thickness increases from top to bottom, and the field, the magnetic field, increases along the x-axis. And what Changping is doing, he's comparing a B20 structure using micromagnetic simulations. He's shown that the skyrmions are stable in that green region at the top. In other words, only for thin layers. Whereas in our D2D structure, which has a lower symmetry, and basically is no component of the Delizinski-Mirier exchange vector in the direction of the magnetization along the tetragonal axis, he calculates that the anti-skyrmions will be stable over independent of thickness. And that's essentially what we find. But we also find something really interesting, that if we look here on the right-hand side, this is the Lorentz image, which is imaging the in-plane component of the magnetization. You can see on the right-hand side, the black and white lines corresponding to left and right going magnetization are closer together than on the left-hand side, which is thicker. And you can even see visually that the helical period is increasing from the right to the left as we increase the thickness, which is shown on the left-hand side. The period of this helix increases from 100 nanometers when the lamella is 40 nanometers thick. It doubles when the lamella is 160 nanometers thick. So we have a very strong dependence of the helical period on thickness. Now, what is that caused by? We would not expect any of the exchange interactions to vary with thickness. And this is actually, we showed, is caused by dipole fields, which play a very important role in anti-skyrmion systems, which is not the case for skyrmionic systems. And in fact, it's even more dramatic. We showed in this paper we published last year by Changping that the period of this helical system, which again I showed you is oriented in one of two perpendicular directions, you see increases as we increase the thickness of the lamella to 1.6 microns, it goes up to 600 nanometers. And I have to say, using a Lorentz technique, which is a transmission of the electron beam technique, we can only go up to about 14 nanometers. So we need to switch to a different technique. And here we're using a variable temperature magnetic force microscope that I also set up here. And it's a fantastic instrument from Attacube, where we can now image not the in-plane, but the out-of-plane component of the magnetization. And shown on the bottom left is a line profile that proves that it really is a sinusoidal variation, and that these really are anti-skyrmion or skyrmionic-like features, not magnetic bubbles. And finally here, here's a series of images in which by controlling an in-plane magnetic field as we saturate the magnetization and then reduce the field to 0, you can see very beautifully that we could reorient the helical structure so that it's either, as you can see, parallel to the long axis of this lamella, this lamella, as you can see in C, is approximately 8 microns wide and 16 microns long. This is some beautiful structures made by another student, Abe Shivinasta. And you can see then we can reorient these helices so they're either along one in-plane direction or another one, or we can see a combination of the two in D. And again, we showed that this helical period systematically and monotonically increases with thickness even up to beyond 4 microns. So a huge dependence of the size of these periods, and at the same time, we can see the size of the antiskyrmions. So here exactly the same lamella, whereby changing the magnetic field, we can see over the whole thickness range from up to 4 microns, we can see antiskyrmions. And visually, you can clearly see that on the left, they're much smaller than on the right-hand side. And again, this is a magnetic force microscopy, but we can also, they're so large, we can use them, we can see them using Kerr microscopy. And so the size increases with thickness. Again, very interesting for device applications. And then another very interesting discovery, which was Jagannath again, another student he discovered, we published last year, which is that in this system of antiskyrmions, it turns out you can form a completely another topological nanoscopic chiral object, which we've called an elliptical block skyrmion. And it turns out these helices, if you see in F, the helical structure can be converted into a series and an array of elliptical block skyrmions. And these the elliptical axis is oriented along one of the two directions in which block walls are favored. But these objects only have block walls, unlike the antiskyrmions, which have block and nail wall characteristics. So this was the first time that two distinct topological spin textures had been found in the same material. So this is super interesting that we could see this again in this Heusler compound. And then, well, here you can see a beautiful image on the top right where we can see in the same time, we can see these elliptical block skyrmions whose long axis is oriented along one of these two perpendicular directions, which, as I said, in the crystal structure of this Heusler compound favors block walls. And then down below, you can see some simulations which are carried out by Berger Goebel at the Martin Luther University. And we have basically what Jagannath has found is that depending upon the temperature and magnetic field, at lower temperatures, you tend to get to these elliptical block skyrmions. And at higher temperatures, you get antiskyrmions. And the reason is we believe it's a competition between a Delizinski-Maria exchange, which is favoring antiskyrmions at high temperatures. And at low temperatures, the dipole energy becomes dominant, and the dipole-dipole interaction favors the block skyrmions. And so we have this perturbation of the antiskyrmions, which become square-like because of this dipole fields, or at lower temperatures, we see basically these elliptical block skyrmions. And as was mentioned in the very first talk today, these objects have topological charges. And so we have the first case where we have distinct topological charges in the same system. We think this is maybe, again, very interesting for possibility of building racetracks. So here, Jagannath has looked at tiny nanowires made of this material cut in different crystallographic directions. And he can see a combination of antiskyrmions and elliptical skyrmions in the same system. And so potentially we could, and I'm going to skip that, we could use this to store information in the different topological nano objects in the same system. This could potentially be interesting. So again, I think for quantum devices, this is very interesting. And I have to say that in these systems, we haven't yet been able to manipulate these antiskyrmions with current. And we believe that we need to do this by growing these films on layers in which we could generate spin currents. That's something we're working on. We haven't yet succeeded, but we think that's potentially very interesting for quantum devices using these objects. But I wanted to finally mention, which is maybe a bit technical, but turns out recently we've discovered that at the edges of these lamella, we see a new object that had not been theoretically predicted. This is just to show you where we're looking. We're looking at the very edge. And I'm not sure you can see this, but this is some beautiful work in the top right with Daniel Loss's group. We're simulating what happens at the edges of these devices. And what we think we're seeing is we're seeing some fractional objects where the topological charge is no longer an integer, but can vary continuously. And this is the first time that these such fractional objects have been seen. And we've seen, Jagannath has seen both fractional antiskyrmions and fractional block skyrmions at the edges of these systems. And we believe it's sort of like a bulk edge correspondence that you need the interior lattice to stabilize these fractional objects at the edges of these devices. So these we think is very interesting. It's the first discovery of these fractional spin textures, and we hope that our paper will be accepted soon. And these are some beautiful simulations of these anti-skyrmions tubes on the right-hand side, plus the fractional objects at the edges that we appear to have detected. And then finally, I wanted to mention that we're of course trying to make high quality ternary films in which we could see these anti-skyrmions. To date, we've only seen these objects. This again is magnetic force microscopy, where we can see the outer plane component, and you can see this labyrinth phase at low temperatures appearing at low fields. This is low temperature. And then at higher magnetic fields, we can see these individual objects. And whilst it's difficult to say in a magnetic force microscope whether they're really anti-skyrmions, it seems from the phase diagram shown on the right, so the orange curve corresponds to where we see these domains and these single phase objects, then it seems to be very close to what we see in a bulk material where we can see antiskyrmions using Lorentz microscopy. So this is something that this has just been published in Advanced Materials, and I think this is super interesting. Again, if you want to make quantum devices with these systems, we will need to manipulate them with current. So I think now, I think I'm running out of time. I was going to talk in my second part about a little bit about Ionitronics, but it looks like I've totally run out of time. And the motivation for Ionitronics is basically neuromorphic computing. But I think I'm just going to have to skip all this. And yeah, as you can see, I totally overestimated the time. And so I'm going to stop and say, well, look, I mostly discussed Spintronics, Racetrack Memory, where there's a lot of new physics that we continue to discover in terms of, in particular, chiral phenomena, like the spin Hall effect, like the Dzerzhinsky-Maria exchange interaction, and like these spin textures, which are super interesting, and we could be used to build quantum devices. And so this is what I wanted to say, basically, that Spintronics really promises novel memory and storage devices with ultra-low energy consumption. The racetrack, which is a really interesting concept, I believe will use current pulses to manipulate single or multiple domain walls. Actually, the most exciting near-term application would be to replace static random access memory, which is a super fast memory close to the computing system, the computing cores today. But it's a very, very large cell, which is increasing at each CMOS generation. So with a single domain wall, 3-terminal racetrack device, I believe we could create a super exciting replacement, non-volatile replacement for SRAM, and that's something we're really working on. In most of my talk, then I talked about anti-skyrmions and elliptical block skyrmions that we've observed in a whole wide range of systems. And the size of the anti-skyrmion varies in size. I really didn't discuss that because of the dipole field. And this is distinct from skyrmion systems. And I did want to mention, we've also seen in iron, germanium, tellurium, we do see now skyrmions whose size varies with the thickness of the exfoliated flake. We've also seen skyrmions in chromium ditelluride, and we've also seen these neo-skyrmions, for example, in platinum manganese gallium, which is a broken symmetry system, although nobody had appreciated that. And of course, unfortunately, Ionitronics, I couldn't really discuss, but that concerns the electrochemical control of the state of matter of highly correlated electron systems, which I believe will promises novel logic elements. So I think then I should probably stop. And if there's time, I'm happy to take any questions. So I'm sorry, I ran out of time. Yeah, so somebody has a question. Lucas.
Yeah, thanks very much for this really nice talk. I have several questions. Maybe let's maybe start with the anti-skirmion system. So
Yeah.
it's actually a conductive material, as far
Yes,
as
conductive, that's right.
Okay, but you mentioned that do you have pinning of the anti-skirmions on some kind of lattice positions, or do you know anything about how mobile they are?
So we don't believe they're pinned because we can move them with magnetic field. So they don't appear to be pinned. And we can also move them by applying temperature gradients. Mm-hmm. So we have connected electrodes to a fibbed lamella and applied currents to see whether they could move under currents. They don't move under currents, but we do see them move under temperature gradients. So they're not pinned.
Mm-hmm. Okay, really nice and interesting. Yeah, so the skirmions that we found in the system that I was presenting this morning, actually we found out that they are nail type. However, also the dipolar interaction plays an important role for the stabilization, which we know from their field dependence. So so it's like it seems to be also an interplay between the two stabilization mechanisms. So DMI and dipolar interactions. Wow. And you mentioned that for the anti-skirmions, the advantage is that if you go from like really thin layers to bulk, that you also get them in bulk, whereas when you go to only thin layer, you only there you are supposed to only get the DMI skirmions. However, like I don't know, it's not clear yet for this compound, but as far as so we don't have data that can say that, but my working hypothesis, or one possible hypothesis, is that they will actually undergo a transition from Neal type skirmions in rather thin systems with a small amount of DMI to like kind of Bloch type skirmions in rather thicker systems.
Okay.
And yeah, so yeah, I just wanted it's basically a comment that I wanted to make.
No, it's I thought your talk was very interesting, and we're super interested in what you were talking about and your technique of this Stixum, I guess Stixum or XMCT, which is a very nice technique to explore. Absolutely. Yeah.
Okay.
Thank you for your comment.
Thanks so much.
Okay. Any other comments? Oh, Bernhard has a comment or question.
No, just a question. I was interested in your fractional skirmion edges.
Yeah.
What does that imply for the stability, topological stability of skirmions? You know, if you have an edge and, you know, you get these fractional excitations, don't they, you know, open up some kind of decay channel for skirmion?
I don't know. I think, as you said, we've just discovered them, so we're still trying to understand what the significance is. And it turns out, as I said, that nobody has seen them before. Probably without, maybe there's one. We found one. Well, the referee said there was somebody in one paper that you could see it in the picture, but they didn't appreciate what it was. It seems. So I think these are very interesting questions. And you know, originally we said this is this boundary correspondence, which the referees also didn't like. But nevertheless, we think it's we want to explore this more. It's just totally new. We haven't, as I said, it's not yet published. Okay. But I thought I would mention it. Yeah.
Yeah. Thanks. Very interesting.
Okay, so I think probably there's no more questions. I think I exhausted everybody. There we are. Anyway, I didn't have time to discuss Ionitronics, but maybe another time one could talk about that. Well, actually, the thing I'm most excited about now is some of our work on triplet supercurrents and potentially manipulating domain walls with triplet supercurrents. That's what we want to do. We haven't done it yet. That's what we plan to do. Maybe.
Maybe can I ask one more question?
Sure.
Like you also presented these Heusler alloys, and especially you showed that if you have I think it was manganese and then some elements, and depending on the element, you had a majority spin polarization that reversed actually, and that also reversed the velocity of the domain wall that was moving. That's so right. How can I imagine that? That's like how does the majority spin actually flip then if you or what determines that?
Well, same like, you know, cobalt nickel iron, it turns out they all have the same polarization of the current, it's majority spin polarized. But in a more complex system like these Heusler compounds, then it really depends on the band structure, the Fermi energy, and which is where the density of states is greater in the majority or the minority. This is the reason.
Okay. Okay.
So it's
So
really
it's
a
really related
detailed,
to electronic band structure, basically.
yes, it should be related to the electronic band structure. That's exactly right.
Okay, cool.
Yeah. Okay.
Maybe one more question to your really first slide. There you discussed that together with Bernevik, you actually have some kind of database where you studied insulators, and then then somehow you cross them, and then you get actually metallic surfaces.
Yeah.
Because the wave function actually sits in between two atoms, something like that.
Right. Yeah, that's right.
Is this actually the same as a topological insulator then, or is it?
No, it's not topological at all.
But so
this is really Andre's work and Yuanpeng Zhu, who's here in the Institute as a postdoc. It's their work really, and they call it an obstructed atomic insulator. And so it's really non-topological, but there can also be topological systems with these surface states, which might also be interesting. So these surface states are really classical, if you like. You form them. It's like, I think Andre would describe it as even a system where you have dangling bonds, right? You have charge, and if the dangling bonds, they overlap, you get a state. It's really a little bit more sophisticated, but that's essentially the genesis. But as you said, there can also be topological, and of course he's also calculated that there's quite a lot of these obstructive atomic interface states can also be magnetic. And so this is very interesting too.
So if you have a metallic surface or conductive surface of a 3D topological insulator, right, with the insulating bulk, or some of these metals that you kind of chop, and you also get kind of an edge conduction. So what is the difference between the what is the role of topology, or is there any loss of robustness? Or
probably it's a very good question. Probably is, you know, topological states are not necessarily robust. Like if you make the surface too thin, they'll start interfering with one another, and it turns out it happens when they're quite thick. So these obstructive atomic interfacer metal states should be more robust because they basically really are at the interface, at the surface. So what we want to do, this is just so far is a theoretical prediction. What we want to do then is based on Andre's theoretical predictions and his co-workers, we want to then take two layers. Like we take, and it turns out it depends on the termination. So different crystal terminations, only certain crystal terminations will have these states. So we want to check it by making thin films and putting a second material on top. And then what we want to do, what you're sort of proposing, we want to maybe interplay an obstructive atomic insulator surface states with a topological material, or I'm actually interested in, can we create interfacial superconductors? You know, we have a metal, and then I want to use a second layer. Actually, I want to use a chiral antiferromagnet, and I want to use chiral magnetic fluctuations to maybe give rise to pairing. This is something that I'm very interested in. It's something we're working on. It's, you know, super unlikely we'll discover anything, but I think it's super interesting. And it turns out that I've always been fascinated by the possibility, you know, in the high TCs that Bernhard has done so much work on. Is it really phononic, or what role are the spin fluctuations, since the host materials are really antiferromagnetic insulators? And can we then deliberately introduce spin fluctuations, and in particular chiral spin fluctuations, which are longer lived, and then combine them maybe with these surface states? This is something we're working on.
Really interesting. Thanks.
Yeah. Thank you. Okay. Thank you for your questions. Anyway, no more questions. So I guess